Well, let's learn about op-amp's external characteristics and build its model by using resistors and controlled sources that we've learned before. Based on these external characteristics, firstly, let's focus on op-amp's transfer characteristic. It's a transfer characteristic when op-amp is operating at the open loop condition. Let UD equal the voltage difference between op-amp's non-inverting input and the inverting input terminals. You should pay attention to the reference direction of UD. For a real op-amp, the relationship between its output and UD can be represented by this curve. For simplicity, we use a polyline to approximate it. The polyline has two knee points. The corresponding value on the x-axis of the two knee points is UDS and minus UDS. We can see that the curve can be divided into three regions. Let's discuss them. The first region is a linear region that goes through the origin. In this region, the absolute value of UDS is less than UDS, and the output is capital A times UD. The capital A is op-amp's open loop voltage gain. We've seen the normal op-amp's saturation voltage, for example, 14 volts, and its open loop voltage gain is 10 to the fifth. Then UDS has a tiny value of 0.14 millivolts. In normal electronic circuits, a noise or interference signal can almost reach such an order of magnitude. The second region is a positive saturation region that's shown here. In this region, UD is larger than UDS. The output UO remains constant. It equals to the positive saturation voltage. The third region is the negative saturation region, that on the left. In this region, UD is less than minus UDS. The output is constant too. It equals to the negative saturation voltage. In this lecture, we focus on op-amp's operation in the linear region, that is, the middle part. When the op-amp is operating in the linear region, the relationship between its input and output is UO equals capital A times UD. Based on op-amp's input resistance and output resistance we've learned before, the actual op-amp can be represented by this circuit model. Its input resistance is Ri and output resistance is Ro. Its output equals the voltage difference of the non-inverting input and the inverting input multiplies the open loop voltage gain. Next, we discuss why the input resistance of the op-amp is very large, usually with the order of magnitude of megaohm, while the output resistance is very small, usually with the order of magnitude of ohm. This is op-amp's circuit model. When op-amp is connected to the external circuit as a load, or a voltage signal is connected to the input terminals of the op-amp, the op-amp can be simplified as a resistor. We use such a simple circuit to represent it. Ri is the input resistance of the op-amp. Us and Rs represent the voltage source signal connected to the op-amp. Obviously, we hope that the op-amp can get the voltage signal as large as possible. In other words, the voltage of Ri should be as close as possible to Us. In ideal condition, the voltage of Ri equals Rs. And in this case, Ri of the op-amp should tend to be infinity. That's why the input resistance of the op-amp should be very large. On the other hand, when op-amp's output is connected to the external load, the op-amp can be equal to a series of voltage source and resistor. You will learn the reason after learning Thevenin theorem in the following lecture. This is a load. In order to get the output voltage on the load as large as possible, the internal resistance of the source should be as small as possible. In ideal condition, RO should tend to be 0. When Ri tends to be infinity and RO tends to be 0, the circuit model of the op-amp can be further simplified like this. In this model, the input resistance is infinity and the output resistance is 0. The relationship between the input and output, which is a simple multiply, is represented by the voltage-controlled voltage source.